My name is Sridhar Balasubramanian. I work at NetApp as product security architect, and my colleague Fred Knight is here. So we both are jointly presenting this topic for KPIO Security Subsystem Class. So we're going to go through what is this KPIO SSC and a little bit of background about self-encrypting drive technology. And then what the extensions are. Fred is going to talk about the standardization work associated with this particular initiative. So we all know that self-encrypting drive is a storage device that incorporates encryption, so for encrypting all of the user data at rest. And at near interface speeds, it performs encryption, and the data is decrypted when it is read. And media encryption keys are generated and held by the storage device. And encryption scope is based on contiguous LBA ranges per namespace basis. Password is delivered in clear, which is also known as authentication key. And the illustration at the bottom, which you are all familiar with, is so you through the security send and receive path that you send the authentication key, then you have a key derivative function which performs the key encryption key, which when you decrypt the MEC, which is stored into the device itself in encrypted form, you unravel it, feed the MEC media encryption key to perform your encryption through the AES engine, and the ciphertext is basically stored into the storage. And plaintext data comes through data channel, the interface speeds. So there's a couple of disclaimers we want to make. It's still a work in progress, and we are working with the NVMe and TCG work groups. TP 4055 is the technical proposal, which Fred is going to talk more in detail about that, its current status quo. And then there's also a spec in draft stage available, TCG Storage Security Subsystem Class. Version 1.0 is out, and draft version is out 101 as of September last year. One important thing is the KPIO SSC is designed in such a way, even though that's primarily targeted against NVMe, but it can also be easily adapted to SCSI devices as well. So what's the concept? So the concept is exactly similar to SED, but fundamentally different in some of the aspects. One is that unlike self-encrypting drive technology, wherein internally the keys are generated, so you have a provision to source the keys, media encryption key, from an external KMIP server. And then on the top, the north side, you see the client A, B, and C. They can have variable set of keys that it could use according to the regions that it has been allocated in the device, storage device. So the KMIP server sends the wrapped media encryption key, which is the client is responsible for inserting into the device, storage device. And then there you have the key encryption key to unravel the media encryption key, and then basically unwrapping it. And then you pass it through the encryption engine to encrypt the data that's coming from client. And then internally you have a key cache, which maintains a tag associated to the keys. So that way, the IOs can use subsequently the key tag to encrypt and decrypt data from the storage device in a non-contiguous fashion. So pretty important that there are a couple of sequences here. First, when you start that, first and foremost, the key encryption key must be inserted first. It basically establishes the secure interactions. What it means is that informing the device, subsequently when I send the media encryption key, those are going to be wrapped with this key encryption key so that you know which key encryption key you need to be using to unwrap the media encryption key. The key encryption key could be namespace specific and inserted into the SED by mapping the key tag. It is the responsibility of the host to map the key tag when it sends the KEK to the approximate when it sends the media encryption key to the device. The media, most important fundamental difference is the media encryption keys are not stored into the non-volatile memory of the drive, and crypto erase can be accomplished by deleting the key from the key server and as well as from the key cache. And this can be accomplished on per tenant basis. So the KPIO Security Subsystem Class consists of a few things. One is, this is from the definition, so a compliant storage device will support some of the following capabilities. One is that it should be able to be discovered, the feature level capabilities should be discoverable via the traditional discovery scheme that NVMe supports, discovery protocol, and some user definable features, including what sort of access control that you should be using, and the key configurations. We are going to go in detail in subsequent slides. And then the user passwords, and then there are some unique behaviors can support, like communication and configuration management as well. So the KPIO SSC use cases, I shouldn't call as use cases, basically the life cycle, if you want to imagine. So first you would start with deploying this storage device and take ownership. So it's basically introducing it into the target system where you want to deploy it. And by changing the storage device owner credential, that it's now made specific for the system where you are going to use it. And you activate or enroll storage device. Basically, at this point, you are going to inject the key encryption keys and the key cache slots, and the authentication credentials are configured along with this. And basically, the access control, similar to SED technology, access lock is configured for key encryption key access as well. So basically, you have to unlock the drive, the device for accessing the KEK, and offers more flexibility to unlock or lock specific ranges, similar to TCG Opal, according to tenant ownership. Then subsequently, you go and inject your media encryption keys. So because prior to that, you have injected already the key encryption key, so now you can securely transport media encryption key into the device with the specific key slots, which are later specified during device I/O. The I/O command need to specify which key to be used for a given specific LBA ranges. And for the purpose of encryption, decryption of relevant user data within the storage device. So when you want to repurpose or you want to stop using the device, so you basically have to erase the key encryption key and as well as purging the keys out of your key cache and plus deleting it from the key management server. So key provisioning consists of specific sequence of ordered sequence, basically. First and foremost, you have to do the key encryption key provisioning. So initially, you set up what you would call as the initial KEK to set up the interactions. Then you do an update KEK to inject the actual key encryption key that you want to use it subsequently. So the initial KEK will be sent in plain text format, and then subsequently you update that with the actual KEK you want to provision. Only a single KEK is being stored at the SED, within the SED, and the device should support unique KEK on per namespace basis. Then you start to provision your media encryption key. That assumes that KEK has been previously inserted because media encryption keys are going to be wrapped in with the KEK and then in TTLV format. If you are using a KMIP server, then you pretty much know that TTLV is the parsing mechanism you have to use. It's a specific object encoding mechanism, and then pass it into the storage device. Then the next step is the key tagging. The media encryption key passed into the storage device can be referenced subsequently for future IOs through the use of key tags. This is the responsibility of the host software. The specific key tag mechanism will leverage NVMe directives when directive type is set to key tag. What are the security capabilities? So, like TCG compatible devices, it shall support password authorities and authentication, and securely downloaded MEX and data encryption key or media encryption key is maintained in volatile memory, not in non-volatile. Volatile memory of the NVM subsystem, therefore purged. When you power off the device, everything is gone, so it assures you the confidentiality. And also, it addresses the current possibility of someone stealing the drive and running away with it, and those kind of situations may not occur in these particular SSC. A storage device complying with KPIO SSC will support full disk encryption for all host accessible user data. So the algorithms again, use depending on the device vendor's choices, AES-256 or XTS, any one of those can be used. KPIO SSC shall support at least 2 security providers, admin SP and as well as the KPIO SP. And initial access control policies are configured at device manufacturing time based on manufacturer specific SPs, created SPs. And it will also support certain personalization of access control elements as well. For example, locking of the SP as well. So the benefits are basically, one is the keys are securely managed and downloaded into the system. And encryption of user data is based on IO command indication which key to be used for encryption of the particular command. And this provides a finer granularity of data encryption that enables following use cases. One is it's easier to support GDPR regulations, basically the right to be forgotten. And then it's easier to support data erasure when the data is spread over multiple disks. And when the data is mixed with other data needing to be preserved, then you want only specific regions to be purged out, and that's also possible with this kind of SSC. Assigning an encryption key to a single and sensitive file or something that the host cares about. So that's also possible here as well. So the next part, Fred is going to talk through about the standardization approach here.
Are you going to go back? Are you going to talk again?
Yeah. We'll do the Q&A.
Yep. Just use the handheld. You keep up.
So I'm going to talk about some of the standardization aspects and what this will look like at the API. The discovery mechanisms are some of the same NVMe discovery mechanisms that exist in the identify controller, identify namespace. But as you know, that's a little bit different than the SCDs. There's no way an identifier to know if a drive is an SCD drive or not. You have to do the security protocol commands, security protocol receive to find all that out. Basically, people were asking for an easy way to tell if it's a secure drive, but they forget that those easy ways are all insecure. So if you trust what Identify is telling you, you can use that. You can also use this as an indicator to decide whether or not to go off and do the security protocol commands to actually use the secure method to do your discovery. So there's ways that it'll tell you what's supported, what's not supported, the granularity of the encryption, the different formats and stuff. But you really need to use the security send and receive commands to actually validate so that you know you have a trusted answer about the capabilities of the device. So the key tag that Sridhar talked about, if you think about what's going on with a 256-bit encryption, here we have some examples of some 256-bit keys. Probably not a very secure example, but it's a set of examples. And you can see that to pass one of those keys in with each I/O would be kind of extreme. We don't have that much space to put in the SQEs. Really don't want to be passing that much data around. And even worse, we'd be passing it in the clear, which is really bad in a secure environment. So we use the security protocol commands, security protocol send, to wrap these keys, to load them in, and attach a tag to them. And then with each I/O, we reference the tag.
You still send them over unencrypted.
No.
Yes, you do.
They're wrapped in a key encryption key as they go through the security send command.
Yes, but any other way wouldn't be that way. There is no secure channel.
I'm not sure what you mean, because you've authenticated with the device. You've got to.
No, you don't fully authenticate. None of the TCG stuff is actually valid against replay attacks or man-in-the-middle attacks.
Okay, well then it's just as secure as what you already have with TCG. It's not. Yeah, we're not doing anything to augment and enhance what TCG already provides. So if you want to take up an argument with TCG, then we can have you talk to TCG. So here's a set where we've got a bunch of things in the cache. So they're loaded into the cache using the security mechanisms provided by TCG. And if you find that cache isn't big enough and you need to change them, you need to have more keys available, then you can just reload a whole new set of them, or you can have some different mix of them. So in this case, key tag 1 and 2 happen to be the same that I had in the first load, and now I've got 100, 1,010, 1,030. Those are different values that got put in. There's different keys for those tags. So you associate different keys with each of the key tags so that you can use them then for each of the commands that you send. So here is from a draft. Don't start writing code based on these values and offsets, because this is a draft. It's still subject to change. But we want to give you a flavor for what's coming and what kind of infrastructure is going to be needed to be able to support this. So we've got in a read command an area where we specify the command extension type. So all of these commands, read, write zeros, the verify command, each of these commands will have a way to specify that index, the key index, the key tag. And from the key tag, the device then knows which encryption key to use. So we've then got the field within the read command where if the command extension type is set to 1 for the key per I/O, then we have the key tag value, which is the 16-bit value per I/O. Each one gets to specify its own tag, which then can reference a unique, within that 64, 65K space, a unique encryption key. So for the write command, it's a little bit, it doesn't have that reserve space. There's already the directives code in there. So the directives can be combined. You can do within a stream, you can have different keys within the same stream, or the same key within different streams, because they're independent parts of the write command. So these are the additions of the information. And so when the spec gets finalized, then you'll obviously know where in the SQE all this stuff specifically goes. But this is what has been proposed at this point in time. Still subject to change. So you do a write command, you specify which LBA, how long it is. You've got a command extension type of 1 and a key value, or an index, a key tag value of 1. And we saw earlier that here's the key associated with key tag 1. So it only takes a 16-bit value, and you specify this big, long 256-bit key that ends up getting used to do the encryption of the data in your write. So there's another write to LBA 200, with 16 blocks being written with using key tag 100. And so again, this is the key that came out of that slide I showed earlier that got inserted into the key cache. And so that's the key that's being referenced to encrypt this data that's being written to block 200. So now if I come along and read LBA 100 and I try and use the key tag number 1, Well, that happens to be the same key tag, so now I'm going to get my data back. It's going to go look up that encryption key and decrypt the data and return the data to me from block 100. If I now access block 200 and I tell it key tag number 1, that's not the right key. So this is a place where we've got a little debate going on in the TCG community and in the NVMe community. Some of the users are saying, well, it would be really nice if you can tell me you used the wrong key. And there is technology that would allow that to happen. The device can figure out. But there's some people that are like, well, there's only 65,000 keys here. To spin through all 65,000 keys, I could just go try them all until I eventually get data that looks good. And so it would be sort of a way to, I mean, what's the point of having the key if you can just guess what the right one is? So that's one side of the argument.
The thing is that it just fundamentally can't work, because this now means you need to store, in the best case, if there is a key in the way these idiots want it, you'd actually have to store which key with each LBA.
That is one way to do it. There are other implementations. One suggested implementation was, do you encrypt before you apply the CRC, or do you encrypt after you apply the CRC? If you encrypt after you apply the CRC, and then you apply the wrong decryption algorithm to it, your CRC isn't going to match. The problem with that is, now it looks like a media error. Just because you supplied the wrong decryption key, all of a sudden, your device is going bad, and it's throwing media errors, giving you CRCs that are wrong. So that's not really a good way to do it either. So there's a whole debate going on about, can you tell whether that's the right encryption key or not? And if you can tell, do you really want to tell the user that it was the wrong one? Or do you just want to go ahead and use whatever the encryption key was they told you to use and give them whatever the result is? It'd probably be pretty hard to make any sense out of it, because it wouldn't be what they wrote. They would just get a gobbledygook piece of data.
Well, it would be very, very, very useful, actually. What Ted said earlier.
Yeah, there are all sorts of security attacks that can take place if you supply information. Any kind of information that you supply can tell them something. If you tell them it's the wrong key, it tells them something. If you give them some bogus data back, then that can tell them something. So there's a whole discussion point going on about what to do if it's the wrong key. So
Do you want to just focus on setting up the kind of the controversy, then we can figure out the controversy in the Q&A or afterwards?
yeah, so that's the point of that one, is that if you supply the wrong key, we're still talking about what to do for that case. But as long as you supply the right key, you can see there LBA 200 using key tag 100. Key tag 100 was what it was written with. So now you get your data back. So we've talked about the security send and receive commands. That's how you interface all of the TCG capabilities. So that's where the loading of these keys would go through the TCG mechanism. That's how you do security receive, is how you do the discovery, how you can do a secure discovery of what the capabilities are, what the different algorithms are. It was how you would be able to purge the cache if you wanted to delete certain keys out of the cache. So the hosts are the ones that are responsible for doing the right thing here. You have to tell us which key tag to use to write, which key tag to read, and then you'll get your data back. So if the host is going to do something wrong and supply the incorrect key, that's one of the cases we're still trying to work through. So if you get an I/O request specifying a key that doesn't exist, that one's not too hard to figure out. We know how big the key cache table is. If we haven't loaded a key, that's not too hard to tell. So we can tell you that, you're trying to do an encrypted operation using a key slot for which there is no key. So basically, we're assuming that the host has done the right thing to inject the keys and to only use the keys that they've injected into the device. So some of the error handling is still a work in progress. What to do if it doesn't match, if you're using the wrong key. And we're assuming that the host is doing the right thing. If it's using the right one. Like I said, we can tell if it's been deleted or if you're trying to use a key slot that isn't the right one. So the technical proposal is very close to being finished, very close to being sent out for member review. If your company's a member of NVMe, then you'll be able to see that very soon. But the TCG work is still ongoing. They're not quite as far along. So whatever NVMe does, it's not going to become fully public until the whole thing is done, until everything is known to work together. We're not going to release half of it and publish it and say, here's how you'll do it, but not give you all of the TCG pieces. So there's still some opportunity for synchronizing between the two and some chances that we'll either find something and have to fix them later or what. Some people have asked about SCSI and SATA. The TCG protocols are the same. So injecting the keys, managing the key cache, that stuff would all be the same. But if you've worked with SCSI and SATA, you know that their commands have no more room left in them. They've completely used up everything in the read command and the write command. So if somebody wants to do this, and you can see what my last bullet says there, if somebody wants to do it, it means you're going to have brand new read commands, brand new write commands. You're going to have a key read 32 and a key write 32, something like that, that somebody's going to have to come along and invent, and that's going to be whoever the interested party is that wants to do that, because right now, we don't have any interested party that wants to do that. But because the TCG infrastructure is all the same, it could be done. So at this point, we're ready for questions. If you want to talk to your NVMe representative, if we want to talk about it at BOF or something like that, about how we can work on supporting this in Linux.
Get TCG out of the fucking loop. It wouldn't make our lives.
We're stuck with TCG because of all of the infrastructure that they already have.
But we're not even using much of that, fortunately.
Thanks. Go ahead.
Yeah, I have two questions actually. So the first one is like from my follow-up from my session. If I want to use it, how can I make sure it works in real hardware?
One of the discussion points that we've been having is, can you read the decrypted data raw? And
Encrypted.
Yes, the encrypted. Can you? The people in the computational world love that idea. They want to be able to send raw data to the device, get it encrypted, and then get the encrypted data back out. They want to be able to use the computes in the device to service their needs.
Yep.
So they really like that idea. The
Yep.
people who want to validate want to be able to write the data, read the data back, and say, did it get the result that it was supposed to get if that algorithm was the algorithm being used, and they can validate the algorithm. So there are good reasons to allow that. There are other people that, well, I don't want to let any of that out. If I leak anything, then I'm creating a way for people to attack the algorithm. Yeah. And so we've got people on both sides arguing.
So the
that
second
it should
people
or
that-
shouldn't
The
happen.
less polite answer is, you need to make sure the stupid monkeys from TCG don't get their way to turn this into something more complicated and broken than Opal, and make sure it stays a simple stateless offload.
Well, if you get encrypted data, basically the basic principle of any cryptography, strong cryptography, is you have everything except the key. So there should be no argument should somebody be able to get the encrypted data back in raw format, because if you use strong encryption and you implemented everything properly, your data is secure.
Yes, but I go back to a meeting that we had in a public open standards committee where the FBI came in and was talking to us about getting data out of drives. And they were worried about over-provisioning in SSDs. How do we get at all of that over-provisioned space where stuff has gotten hidden? That's what we need to see. And we were like, well, what about the self-encrypting drives? Don't you care about that? And they were like, oh, that's irrelevant. We just make a copy of that raw data. We put a couple of thousand CPUs at attacking it, and it won't be long before we get it. And that guy that's looking at that porno stuff, he's going to jail. We're going to get him. We don't care about encryption.
Okay. I think we crossed a certain line.
That's your threat model. We don't need any of that anyway.
So,
That was a public meeting and a public statement. So.
thanks, Fred.
Yeah, can I get some clarification? There's a thing called bands in, I think it's in TCG Enterprise, which kind of sort of related to same use case. Maybe I'm missing it. So how is it different, a use case for a
I think
TCG?
the bands are LBA based.
LBA based.
They're
Yeah.
LBA based, right. Whereas
Yeah.
this is per IO. So you have an application that's accessing data for Bob, Harry, and Sally. And, you know, Bob gets one key, Harry gets a different key, and Sally gets a different key. And so when Bob comes along and says, hey, I want to be forgotten, you go to KMIP and say, hey, KMIP, forget about Bob. All of a sudden, Bob's data's gone.
So you can't do that by giving Bob, Harry each different band?
You can.
You can.
But then you've affected your block allocation. You've had to pre-reserve certain amounts of space for Bob and Harry and Sally. It becomes a different kind of complexity.
And you have another really big difference that matters almost even more, which is with the in Opal it's locking ranges. Maybe the old enterprise TCG had SSC had a different name, but it doesn't matter. The one thing is you have a very limited number of those in a given drive. And with this one, you have a limited number of active keys, but you have an unlimited number of passive keys. They're not in use for the encryption, decryption operations right now, but can be on the drive.
Right. You can have millions of them in the KMIP database, but you can only load 64K at a time.
All right, so I think Ted was patient.
So I just had a quick question here, which is, I understand that performance issues are largely irrelevant to standards committees, and it's very, very early. Yeah, I mean, performance is out of scope of SCSI, right? I've heard this a million times. It's a great excuse. And it's very, very early, but what sort of performance numbers are we hoping to be able to get from this? Because, you know, as a guy in industry, I kind of care about performance.
I would hope, participating on the standards committees, that the goal would be the same, that we continue operating at a media speed, we continue operating at wire speed, that this does not slow things down. That would be my hope and my goal, because I also work in the industry and I have to sell things to people that are going to want to buy them, and if they're running really slow, then that would sort of defeat that purpose.
Okay, so why don't we thank Fred and Sridhar, and then we will continue.
Thank you.